Howdy, folks. So today we're going to go ahead and talk our way through Chapter 1's materials, which is really just giving us the basics of muscle physiology. So first we talk about what is a muscle fiber, which is going to come down to the individual muscles themselves, the myofibrils. So now we're going deeper into all of the individual sarcomeres and then how we get a muscle to contract. We've got our different muscle fiber types, okay? Now this is going to come down to things like fast twitch muscle fiber, slow twitch muscle fiber, type 1, type 2A, and type 2X. The type 2s are our fast twitch, the type 1 is our slow twitch. Now, we then have different types of muscle. Now, we've got skeletal muscle, and that's what you can see pictured in the upper left, and that's just the one that we use to contract and move our bodies. We then have smooth muscle, which is going to be all type 1, and that's what's going to be around our intestines, around our arterioles and arteries, which are going to relax and contract to dilate or to constrict. And then we've got our cardiac muscle, which is all type 1, and that's in our heart. And obviously that's what's causing it to beat every single moment of every day for our entire lives. Now, those individual muscle fibers, how we're going to recruit them by our nervous system. Our slow twitch fibers are going to be innervated by slow twitch motor neurons, and those individual motor neurons are going to recruit 10, maybe 100 individual slow twitch fibers. Whereas our fast twitch motor neurons are going to activate possibly hundreds into the thousands of individual fibers. So we're naturally going to get a much greater force production whenever we tap into our type 2 fibers. And we do this in an orderly system, sometimes known as Henneman's size principle, where we're going to go ahead and tap into our slow twitch because they're the most aerobic, they're the slowest, but they're the most efficient fibers. And then as we need to produce more force and specifically power, we're going to tap into those type 2 fibers. And then we're going to talk a little bit about fiber type and how that's going to be related to athletic success. So let's keep on going through. Now, the actual muscle fiber, around it all, we have what's known as an epimyosin. Sometimes people refer to this as fascia, this is connective tissue. We then have our fasciculi, which is going to be individual, essentially groups of fibers that are going to be surrounded by a perimysium. And then inside of this, we have the individual muscle cells. And then the muscle fiber itself is going to be surrounded by an endomysium, so it's another thinner layer on the outside. And this is where we have the individual myofibrils, which are going to be divided into the basic contractile unit known as a sarcomere. So when we're all the way down into those individual fibers, we're going to have the cellular membrane of our muscle fiber. Now, this is important for two reasons. One, structural integrity, and then two, conducting action potentials to get that muscle to contract. So what it's going to go ahead, at the ends, it fuses with the tendons, and that's obviously what allows us to contract. So all these little individual sarcomeres are effectively just going in series, end over end. Parallel is cross-sectional area, and that's what we're going to increase in parallel whenever we're doing resistance training. Stretching a muscle can increase the number in series, hence the length of it. Now, this is also important for maintaining our pH and for also getting nutrients into and out of the cell. We also have what's known as satellite cells. These are the stem cells specific to muscle that will become activated and then go ahead and fuse with fibers in order to help with growth, development, along with recovery from injury, immobilization, or obviously excessively hard training. Now, inside of the sarcolemma, we have what's known as T-tubules, and there's going to be a little hole that you see that goes into the cell, and that allows the action potential to travel to what's known as the sarcoplasmic reticulum, which is where we're going to store calcium during rest. Once that action potential goes in there, the calcium is going to release, going to go into the sarcoplasm. It's the cytoplasm, this is effectively the cellular fluid inside of the membrane of the muscle cell, and that's what's going to eventually bind to troponin and help us lead to contraction. But we're going to get to more of that in a little bit. We also have our mitochondria, the powerhouse of the cell. Type 1 muscle fibers are going to have a lot more mitochondria, but you can also increase the mitochondria in your fast twitch fibers by doing aerobic style training specifically with those fibers. Now, we talked about sarcoplasm just a moment ago. Once again, that's the cytoplasm, but this is also where we're going to store lots of glycogen, where that's the storage form of carbohydrate that we're going to use for energy, and myoglobin, which is the specialized form of, essentially, it's a modification or a change of hemoglobin. So it's what is going to bind to oxygen, take it from the bloodstream, and deliver it to the mitochondria for aerobic metabolism. And those transverse tubules, aka T-tubules, which is going to allow for that action potential to move rapidly through the cell. calcium in the sarcoplasmic reticulum is going to be stored or bonded to what's known as calsequestrin. When the action potential travels into the sarcoplasmic reticulum, the charge is going to change the configuration of calsequestrin, and that calcium is going to in turn leave the sarcoplasmic reticulum. So the individual myofibrils, remember, are going to be in hundreds and thousands of number per individual muscle fiber. Now, it's going to break down to the basic unit, which is a sarcomere. Okay? Now, the sarcomere has got actin strands on either side bracketing it, and then the myosin is going to be in the center. Myosin is what actually grabs onto actin and pulls it in towards the center. So the Z lines is where you have actin on both ends linking together, and whereas the myosin is going to be pulling the actin strands together. And what's going to be happening, since they're all in series, they're going to be pulling together in all those gaps, and that's what gives us the collective shortening of the muscle. Now, that alpha motor neuron, that is what's giving the signal from our brain all the way down to our muscle to get it to contract. And we're going to find that it's going to cause every single fiber that it touches to contract. It can't pick only half of them or a third of them. It's all or none. So every fiber that that individual motor neuron touches is going to have the action potential travel to it, which is going to give us maybe a little muscle twitch, maybe a full tetanus, but it is going to cause those fibers, all of the fibers that innervates, to actually contract. And the place which this actually occurs at is what's known as the neuromuscular junction. This is where we're going to have that electrical signal convert over into a chemical signal through neurotransmitters, specifically acetylcholine, which are going to travel across the neuromuscular junction and bind to what's known as the ligand-gated receptors. And that's going to allow sodium to go into the cell. And if enough goes into the cell, it opens the voltage-gated channels, and boom, we got an action potential, and it's going to travel along the sarcolemma. Now, here's that example of that slowly increasing amount of force from sending one signal, so we get a twitch. If we send a couple signals before the muscle can fully relax, we're going to get a summation. And then if we just keep sending all of these stimuluses in a row, we're going to get this tetanus, where we're going to get maximal force production for the individual fibers that are being activated by that motor neuron. Now, this is one of the most important things to understand, and this is how muscle contracts. Like anything, when you guys are watching these, listening, or obviously in here with the class, please, please, please hit pause, go back, play it again. Hit pause, go back, play it again. The more times you expose yourself to it, the better this is going to go. So the alpha motor neuron is going to get the action potential, goes to the end of it, where that's going to cause the release of vesicles filled with acetylcholine. That acetylcholine is going to float across the neuromuscular junction, bind to those ligand-gated receptors. When they open, sodium is going to start coming into the muscle cell until eventually the level of sodium, the charge, changes enough that we hit that threshold. When that threshold is hit, now we're going to open the voltage-gated channels. And this is going to open the voltage-gated channels as it travels across the sarcolemma down into the T-tubules. Once it goes into the T-tubules, it is going to then transfer through the DHP and ryanodine receptors into the sarcoplasmic reticulum. This is going to cause calcium to be released from calsequestrin. Calcium is then going to go into the sarcoplasm. That calcium will bind to troponin. Troponin is going to move tropomyosin off of its covering of all of the binding sites on actin. And at that point, myosin is going to go ahead and grab hold. It's going to, from there, ratchet itself forward. ATP is going to go ahead and drift in, cause it to relax and spring back. And then it's going to grab again and spring forward. And it's going to be bringing those Z lines closer together as long as calcium is available. Now, once calcium, not enough action potential is being sent, calcium is going to be pumped back into the sarcoplasmic reticulum through the calcium ATPase pump, and from there, the muscle is going to relax. So this is where you can actually see those actin strands being pulled in through the center line. Myosin is what causes contraction, not actin. Actin is passive. It simply is going to be pulled into the center. And from here, we have that myosin cross-bridging. When I talked about how ATP is going to go ahead and bind, cause it to go ahead and release, it will then hydrolyze, causing it to spring back. And from there, it's going to grab and then ratchet forward and keep going as long as energy is available. Now notice ATP is needed to get myosin to let go of actin. This is one of the mechanisms that can cause cramping. And also, we've obviously talked about how you need calcium, and specifically, you need to be able to change the electrochemical gradients enough to go ahead and get the muscle to both contract and relax. Hence why your electrolytes matter. You need calcium for contraction, and you need ATP for relaxation. And then we have our different fiber types. Our type 1 fibers are very oxidative, aerobic. They're really good at doing long distance work, things that require just consistent effort. They can use fats as fuel aerobically. They can use carbs as fuel aerobically. And the higher the intensity, the more they're going to drift towards more carbohydrate. We're going to get into that more with chapter 2. Now, your type 2 fibers are going to be really anaerobic. And so they're going to use glycogen and or ATP phosphocreatine, our shortest energy system, in order so that we can keep up that energy output for whatever we're doing. They're going to produce a lot more power. They literally are more powerful than our type 1 fibers. When you compare the two and they have the same cross-sectional area, there's no difference in force production. Our type 2 fibers are more powerful. That's the key difference. And we're going to go ahead and find that training is going to cause a certain amount of changes in these fibers, and that we have what's known as hybrid muscle fibers. So it's not like your fibers are just plain type 1, plain type 2A, plain type 2X. We're going to have fibers that are type 1/2A, type 2A/2X, and even some that are type 1/2A/2X. Training and or not training is going to cause us to convert to one or another. Aerobic style training converts us more to type 1 fiber. Strength power style training is going to convert us more to type 2A, and doing nothing and being a slug is going to convert you more into 2X. So we have a certain amount of plasticity. Our fiber type is 50% genetically inherited, but after that, the other 50% is how do you live your life? So if you're going to do more of aerobic style training or resistance training, we're going to see the fiber type shift towards whatever you happen to be doing more of. Whereas your Usain Bolts, your real freaks of freaks athletes, those folks were born with a genetic complement that obviously set them up to be very successful in specific endeavors. Another important property to understand with muscle is the more overlap we have with the actin and the myosin, the greater the force production. And this gives us what's known as the length tension curve. This is what you observed or will observe in lab number 1, where we're going to find when we have the optimal amount of cross bridging, where the greatest amount of actin and myosin heads can interact, we're going to have the greatest force production. So if we're in a stretch position where we barely have a lot of overlap, we're not going to produce a lot of force. But at the same time, if we have the actin strands starting to butt up against each other, we're in the shortest position, we're not going to be able to produce that much force also, because we literally have not just obviously a lack of overlap, but literally we can't go any further. So we're going to find there's an optimal point. Now, this is the active component of muscle force production. We then have a passive component, which is really putting a stretch on a muscle. And you can feel that intuitively when you stretch a muscle out. You can feel that elastic, or you just really try to stretch yourself. You're going to find yourself being stuck unless you pull yourself down or you put a little bit more weight in your hands, on your back, etc., to pull you into a greater stretch, because the passive component is not going to let you go any further. So all of those are going to be contributing to how much force we can produce. Now, another key component, and this comes from Archibald Vivian Hill, and one of the most important factors when it comes to training an athlete and or yourself, which is the length tension, the force velocity curve, which is the faster we're going, the lower force we can produce. The slower we're going, the greater force we're going to produce. And if we are also moving eccentrically, so that means we're going to be lowering a heavy load, we are actually even stronger. We can lower a heavier load than we can hold still. And we can hold still a weight that's heavier than we can lift back up. Just watch bros bench pressing at a rec center, and you will see this example at one point or another when someone bites off a little bit more than they can chew. So when we're working with athletes, if we get someone stronger, we're going to shift effectively this entire curve up. If we're doing plyometric style movements, we can start to shift it, lengthen it a little bit more to the right. And those properties are going to help us be a better athlete, and why we need to be training these different components in order to optimize our performance. So make sure you guys understand how an action potential works. Make sure you understand the difference in the muscle fiber types, the different components that are important in skeletal muscle, and especially that plasticity, because that's going to play into how, when we're training individuals, another reason they're going to change, and those satellite cells and how they're going to also affect recovery from exercise. And turns out hard training is going to make that happen. So thanks for listening, guys. Stay safe out there and have a great day.